here we go. This is our first lecture on gases. The first thing that we want to talk about is the kinetic molecular theory. And the kinetic molecular theory, this is a theoretical basis that we use to explain the way gases behave. So you have to memorize these. You've got to know these things. And basically what it does is we say, look, if we have a container that has gases, here's what we can say about the particles in that container. So first of all, you've got many particles moving at random. They're really far apart, as we've kind of drawn this picture. And they're not like programmed to move in a different direction. They just travel in a straight line until they hit something. And then when they hit something, they bounce off of it and travel in a different line, right? But everything is random. Okay, the amount of space occupied by the gas particles themselves is much smaller than the amount of space between the particles. So you really do have a lot of empty space between the particles. In fact, when you take 1 milliliter of water and evaporate it, you'll find that it will occupy 1 liter of space. So that tells you that actually, insofar as, how much empty space is there between the particles, it's about 1,000 times as much empty space as you have particle space. Next, we see that gas particles do not have appreciable attractive or repulsive forces. So we talked about intermolecular forces on exam 2. And what this is basically saying is that it doesn't matter whether your molecule would normally be considered polar or nonpolar. If they are so far apart from one another that they don't see each other, then they can't be attracted to each other or repelled from each other, right? They're so far apart, they don't even see each other. And even if I would have hydrogen bonding in the liquid phase, in the gas phase, it doesn't even compute. It doesn't contribute at all to properties. Next, we talked a little bit about this chapter 7. Kinetic energy is proportional to the temperature, right? The temperature is kind of a measure of movement energy, and kinetic energy is a kind of movement energy. So as the temperature goes up, the energy of the particles goes up as well. And finally, we're going to say gas particle collisions are elastic. And that means if we bounce off the wall with a certain amount of energy, we come off the wall with a certain amount of energy. If we collide with each other, we come away with exact as much energy as we had. This is different than at the macro scale, right? If I bounce a ball on the floor, then some of the energy of that moving, bouncing ball gets transferred to the floor with each bounce. And after a couple of bounces, it's going to stop bouncing, right? But when we are looking at the atomic level, we know that energy is conserved, right? When those two particles collide into one another, none of that energy is lost. It might be transferred from one to the other, but it's still there, right? So the collisions are elastic. That also kind of tells you if you've got, this gas cylinder that's full of gas particles at a certain temperature with a certain amount of kinetic energy, if you let it sit over time, the temperature isn't just going to get lost as they lose kinetic energy because they have inelastic collisions, right? Because the collisions are elastic, therefore that kinetic energy is maintained, the temperature will be maintained. Does that all make sense? Well, Erica has a great question. She says, are you going to go into more detail? Yes, we will go into a little bit more detail as we look at mathematical relationships that we observe and try to explain them using the kinetic molecular theory. The only other thing that I would add right now is because your space between gas particles is so large, is that gases end up being compressible. This is something that you cannot do with liquids and solids, right? But you can compress gases into it like a smaller chamber by pushing those particles closer together. And that's how you get things like an oxygen tank that you could hook onto the back of somebody's wheelchair, right? Or a helium tank that you could hook up to the MRI instrument at the hospital, that kind of a thing. All right, well, let's then talk a little bit about the math and the quantities that we're going to be looking at. So for gases, the quantities that we look at are pressure, temperature, and volume. All right, so pressure is represented by P. And it is essentially the force exerted on an area. So where this comes from in terms of gases is every time one of these particles collides with a surface, that it exerts a force on that surface. Okay, so just like if I were to walk up to you in class and I was to poke you with my finger, you would feel that force from my finger poke, right? And if it was a tiny gas particle, you probably wouldn't feel it. But if there were billions and billions and billions of tiny gas particles constantly striking the surface of your body, you would feel it. And in fact, that actually happens, right? You don't feel it when you're at normal pressure because your body is already acclimatized to it, right? But if it was very windy outside, you walked outside, that wind could, depending on how windy it was, it could push you over, right? It could exert a force. And all that wind is billions and billions of tiny gas particles moving rapidly in one direction. Does that make sense? Okay, units that are usually used for pressure, and there's like a whole bunch of them, but you'll see something like PSI, that's pounds per square inch. And I like to bring that to your attention because it really makes sense to see, okay, the force is measured in pounds and the square inch is the area that you're measuring that on, right? So for instance, normal air pressure is about 14 pounds per square inch at sea level. So that's what your body is feeling over every square inch of your body. If you're sitting in a normal room with normal pressure, then that's the amount of pressure that your skin is feeling, that your body is feeling, and it's well adapted to that. In fact, if I put you in an area that had a much lower pressure, it would actually be very bad for you, right? Like if you were in outer space, you would die. All right, so that's normal air pressure. We're not going to use PSI. Instead, we'll see things like atmospheres given by ATM. And 1 atmosphere's worth of pressure as a unit is basically the pressure exerted by air at sea level. So 14 psi is the same as 1 atmosphere. And we'll also see millimeters of mercury, also known as torr. This is, it was originally often, pressure was measured by these millimeters of mercury, almost like a thermometer, but it was a barometer. And the mercury would go up in the barometer and you'd have these millimeters of mercury that it would move up and down. And we see that 1 atmosphere is equal to 760 millimeters of mercury. And I will give this to you. You do not have to memorize those conversion factors, okay? But we'll use, in this class, when we are looking at pressure specifically, we're going to use atmospheres and millimeters of mercury. These are the units that we're going to use and convert between. Okay, does that kind of make sense? You with me so far? Pressure being an important measurement for gases because gases exert pressure on the surface of the containers that they're in. So the mmHg, actually that means millimeters of mercury. Good question, Zach. Also known as torr, yeah. Okay. All right. So next we've got to talk about temperature. Temperature is an important constant to look at, or variable, to look at in gases, because as we see, the kinetic energy of a gas is directly proportional to the temperature. So the temperature here is going to be important for helping us understand the kinetic energy of the gas particles. And of course, T for temperature given by T. This is represents kinetic energy of the gas molecules. Now, there's something really important that we're going to have to note here, and that is, even though you can use Fahrenheit and Celsius, we really want to use Kelvin, because again, it cannot be negative. So we're going to need to know how to convert between them. And again, I give this to you. It's all on the worksheet. It's all in the equation sheet. So you don't have to have this memorized. But this is kind of the Kelvin scale has the same degree size as the Celsius scale. It's just offset so that absolute zero is 0 Kelvin, and then you can only ever be positive. And the reason is that, again, temperature or heat is reflecting movement. So there is a bottom to this scale where you're not moving anymore. You can't have like a negative movement, right? So if you stop moving, then you're at 0, and that's what it is. Okay, so 0 degrees Celsius, which is the freezing point of water, is still 273 degrees above absolute zero. Does that make sense? Okay, so 0 degrees Celsius would be the same as 273 Kelvin. And 0 Kelvin, which is absolute zero, the coldest you could get is negative 273 Celsius. Okay, and finally volume. This, I think, makes sense. Gases take up space, and we represent space by V for volume. So this is V. Measure of total space occupied. And your standard unit for volume is the liter, but you can also see milliliters. And of course, there's also the standard American units of like gallons and quarts, but we're not going to touch on those in this section at all. One thing that you should know, if you didn't already know, that centimeters cubed, cc, equal to 1 milliliter, 1 cc. So that's a measurement, fluid measurement that you'll often use in the hospital setting. That's where the milliliter comes from. Okay. Does this all sound familiar? Does this all make sense? I missed it, but Nicole said that you guys use millimeters of mercury as a measurement of blood pressure, right, in the hospital. So when somebody takes your blood pressure, they report it in millimeters of mercury. So the pressure there. That's right. Okay. So far, so good. So the first thing I have you guys doing, because you're going to have to do it a lot in this chapter, is to do some simple conversions between pressure and temperature and volume. Not between pressure and temperature, but between different pressure units and different temperature and volume units. Let's see here. Okay, so this is just from your worksheet. Number 1, perform the following unit conversions. And here we've got from degrees Celsius to Kelvin, atmospheres to millimeters of mercury, liters to milliliters, so on and so forth. Okay, so let's do this one. Degrees Celsius to Kelvin. How am I going to solve this problem? Perfect. Nicole says, I'm just going to plug it into this lovely, handy, dandy formula. And I want Kelvin, and I'm given degrees Celsius, 23.5. So I'm just going to like stick that right there, right? Insert that for that. So 23.5, 273.15, 296.65, and now actually the significant figures do something interesting here. They say you know the 10th place, but you don't really know the 100th place on this number. And so whatever that is, you add it together, you really have no idea what the hundredths place is in the product. So you should round it to 296.7. Again, I'm never going to test you on that, but that's what Mastering Chemistry is going to tell you. Well, that was pretty simple. Were you guys complaining about algebra? Because this is part of what we mean by algebra. We can do this. You got it. Okay. How do we solve the next problem? 2.35 atmospheres to millimeters of mercury. Yeah, let's see here. We're going to use, Nicole, I think you're right that we're going to use this conversion factor. But whether I multiply or divide, I'm going to let dimensional analysis tell me because I can't remember that. It's not worth my time. But I can say, okay, if I'm starting with 2.35 atmospheres, and then I'm going to convert that using this guy. I want atmospheres on the bottom, so that's going to put the millimeters of mercury on the top. Yeah, right on. If I do that, my atmospheres cancel. I'm left with millimeters of mercury, and I can plug it in. So you can see these aren't necessarily difficult, but the trick is to know which formula to use or which method to use to solve what. 1786. So in this case, I used dimensional analysis, whereas in the first one, I used algebra, right? And we've done a lot of work with both of those systems in this class, so it's kind of like, oh, which one do I use? Does that make sense? Nicole, did that answer your question as I was doing that? Perfect. Okay, you've got that. All right, 2950 K to degrees Celsius. What shall we do here? Yeah, so again, when it comes to Kelvin and degrees Celsius, we've got this handy dandy formula. So that's okay, we're going to do algebra with a formula. Whereas when it came to atmospheres and millimeters of mercury, we saw we have an equivalency. So that kind of tells you, oh, all right, maybe I ought to do dimensional analysis with that. It's not a formula, it's just this is equal to that, right? Whereas this has got several different things in here, variables that you've got to plug in. Okay, so we're going to plug in on this equation, and we've got 2950K, so we'll put that right here. Now we solve for degrees Celsius. So to do that, I'm going to subtract 273.15 on each side. So minus 273.15 on that side, and subtract 273.15 on this side. When I subtract them on both sides, these cancel essentially. And then I say 2950 minus 273.15 gives me a degrees Celsius of 2680 if I'm rounding that appropriately. Celsius. Does that make sense? Whoops. Yeah, that's a high temperature. Erica says that's a lot. It's a high temperature. It's still not high enough to cause your diamond to decompose. So people have gotten higher, but Yeah, it's a funny story. So when you look at things like, remember all the way back to intermolecular forces, and we said, look, water melts at 0 degrees Celsius. Oops. Should be a 0. And that has hydrogen bonding. So that's like way stronger than something like CH4, which has a melting point because it only has London dispersion forces. So it's going to have a much lower melting point, right? So melting point of CH4 is, I have to look it up here. I don't have it memorized. Who has that memorized? Go negative 183 Celsius. Right, London dispersion forces. Okay, whereas this one has hydrogen bonding. And so that's the difference. They're about the same size, but it's that those intermolecular forces. And then we said on top of that, you might have NaCl, which has a melting point or a, you can get that to melt at about 800 degrees Celsius, which is huge, right? That's because it has the ion-ion forces, which are really strong. And then at the very top, we had a diamond, which has a melting point of 3000 Celsius, because that is a covalent network solid. Do you guys remember all this? You still need to remember it. It's all going to be on the final. But it's also a little bit appropriate for this chapter as well. So we're talking about gases, but the properties of liquids and solids as they convert to gases and so on and so forth. That's pertinent, I think. Anyways, so the interesting thing, I mean, one of the interesting things about this observation is that you just know the only way to know that the diamond has a melting point of 3000 degrees Celsius is you know that there was a scientist that had to do that, right? He had to get a diamond and then get it really hot and like measure it as it was getting hot until it decomposed. For science. Right? So if you like diamonds and you think, wow, that's expensive, then yeah, it is, right? But of course this is science, right? So if one person did it, then somebody else had to verify it. And that one person might have done it a couple times to make sure that what he did wasn't a fluke and like kind of narrow in on that degree set. So several diamonds were sacrificed for science so that we could determine that in fact it does decompose at 3000 degrees Celsius. And if you didn't know what diamonds were made of, then that's a really great, this is a really great thing to see, because then you see it basically forms into a lump of coal and you go, oh, diamonds are made out of carbon. Who would have known that, right? They don't look like carbon. They don't look like any other form of carbon we're familiar with, right? They don't look like graphite. They don't look like coal. So it's weird to see it in this form, right? And you might think, well, that was really sad that they spent all that money just to discover that they turned it into coal, which is worthless. But, you know, it all has to do with your attitude, right? You could say, I learned something new for science and that was worth the money. Or if you are particularly enterprising, you might find a rich businessman and say, I have strong evidence the diamonds are made of a very common and cheap material. And if you will finance my research, then we can together find a way to turn coal into diamonds and we will make a lot of money, right? That's the correct attitude to have, right? So, yeah. I mean, coal is pretty cheap. So if you could use it to make diamonds, then that would be great. And it took us a long time to figure it out, but there are several companies now that know how to make diamonds. I'm not sure if they use coal anymore, or they use other sources of their carbon, but it's interesting. Anyway, sorry, that was totally an aside. That's nothing to do with what we're doing down here, but yeah. I wasn't sure if we'd had that conversation back then. I think we ran out of time and I wasn't able to talk about how awesome diamonds are or the scientific method. Wanted to make sure that I snuck that in there. Okay. Let's do this next one. Negative 69.5 Celsius to Kelvin. Anytime, Erica. Anytime you guys want me to go like off topic and give a big tangent on how awesome science and chemistry is, happy to do it. All right, how are we going to solve this problem? Yeah, we're just going to take this guy again. And then we're going to insert. Okay, this is the degrees Celsius, so I'm going to put this in that spot. And we're going to solve for K. 273.15 minus 69.5. So I'm going to get 203.7. That's my answer. Perfect. You guys have got it. Okay. How about liters to milliliters? Do you guys remember how to do that? Yeah, you guys have got it. Okay, so you're going to use a conversion factor that you have previously memorized, right? That 1 liter is equal to 1,000 milliliters. You could also use that trick, 1 liter is equal to 1 liter, and say, okay, milli is equal to times 10 raised to the negative third, whoops, times 10 raised to the negative third. Both of these conversion factors are the same thing, and they'll get you to the same product. So whichever one of those you prefer is fine, but if you're starting with 0.200 liters, and we're just going to do dimensional analysis using those conversion factors that you've memorized. Cannot forget them. We'll see there's 1,000 milliliters in 1 liter. Liters cancel. And we're left with 200, right? 200 milliliters. And I can plug this in here. 0.2 times 1,000 is 200. Guys, remember how to do that? All right, last one, 450 millimeters of mercury. Convert that guy to atmospheres. What are we gonna do? Yeah, 450 millimeters mercury. Then use our conversion factor here. We know that 760 millimeters of mercury is equal to 1 atmosphere. Okay. Right. And then, of course, we note our millimeters of mercury cancels. So when we plug this in, we're going to get 0.592 atmospheres. Okay. So this is a really nice kind of introduction to the units that we're going to be using and converting between them. Hopefully you guys feel pretty comfortable with these. Any questions on them? Okay, lovely. All right, then let's move on. And we're going to start talking about individual gas laws. So individual gas laws are gas laws that were discovered. Gas laws, these are observed relationships between these units, pressure, volume, temperature, amount, which I'm going to represent as N for number of moles. Relationships between these that were observed, and scientists found was that these were pretty universal. It didn't matter whether the gas you were measuring was air or whether the gas you were measuring was just oxygen or just carbon dioxide or just nitrogen or whatever, or if it was a mixture, it doesn't matter. They all behave the same. And we have very distinct, interesting relationships between these variables, all right? So we'll start off with this one. They all have names based on who discovered them or who they decided to give credit for. I'm never going to test you on the names because that's not chemistry, it's history. But for the moment, we'll address these by their names. So the first one is Boyle's law, named after the English chemist Robert Boyle, who studied the relationship between pressure and volume. And what he found is that for a sample of gas at constant temperature, so at constant temperature, so if we're not looking at temperature at all, it's not changing, then we find pressure and volume are inversely related. Okay, that's a bunch of words. So there we go. What this means mathematically is essentially that pressure is directly related to the inverse of the volume. So 1 divided by the volume. So as your pressure goes up, your volume goes down, essentially. As your volume goes up, your pressure goes down in a fixed system. You guys are actually all pretty familiar with this, even if you don't think of it, because if you ever had your hands on a syringe, not a needle, but just a syringe even, then you've played with it, because that's the human thing to do with a syringe, right? I tell you, my kids, get your hands on the syringe, they're like, hey, this is the funnest thing in the world. Okay, so here's your syringe, and that's the little spot where you might attach a needle. And you've got some sort of a plunger here, right? Okay, so the first thing you do is you pull out the plunger so there's some air in it, and then, because you're human and you're curious, you stop that thing with your thumb, right? And then you try to push down on it. So this is taking a sample of gas, it's at a constant temperature, and you are lowering the amount of volume that is there by pushing the plunger down. What happens to the pressure if the volume goes down? So if the volume goes down, what happens to the system? The pressure goes up. You can feel it on your thumb. It's trying to push it apart, but you have to hold it in really hard because this is fun, right? So you push it in, and then when you decide you're bored with it, you take off your thumb, and what happens? It releases all that increased pressure. You get a out the end of that syringe, right? Tell me you've never done this. Come on. I swear. I don't believe you. I think you've all done this before. And after you do this first one, you're going to do the opposite, right? You're going to push that syringe all the way in, then you're going to plug it, and then you're going to try to pull the syringe out with your thumb plugging it. So in that case, you increase the volume of this closed system at a constant temperature, and what happens to the pressure? The pressure decreases, right? And the plunger wants to kind of, there's actually pressure on the outside of the plunger from air on the surface that's trying to push it back in, right? So that it's back to equilibrium, so that both sides have the same pressure. So, and you can feel that it wants to kind of suck it back in where you're trying to pull it out. And after you do that for a couple seconds, then you're going to take off your thumb, and it goes and pulls that air in, right, to to offset the vacuum that you had created of low pressure. Does this make sense? Okay, so if you're ever like, this is a very simple expression of this law that I'm pretty sure you've all observed. It is fun. It does entertain you for a little while. I mean, I'm an adult and I've done it lots of times, but still, if I see a syringe on the counter, it's kind of tempting to pick it up and play with it. It's fascinating. Okay, so the pressure is inversely related to the volume. Well, we can't do math with this tilde. We need an equal sign. So essentially what this means is that your pressure is equal to some constant. We're going to call it K. It doesn't matter what it is. Times 1 over the volume. That's what takes it from being a mere relationship to an equivalence, right? So it's direct, it's inversely proportional, or it's equal to some constant times that inverse. The next thing that we do with this equation is, now that they're equal, we're going to move the V over, multiply both sides by V, and you get this one. PV is equal to some constant K. Pressure and volume are always constant. Well, that means that your pressure and your volume at your initial conditions are going to be equal. If they're constant, always constant, that's going to be equal to your pressure and your volume at your final conditions, right? So as you change a system with pressure and volume, then we find that the initial pressure times the initial volume will be equal to the final pressure times the final volume. Again, this is at a constant temperature. And this is just, again, showing us this relationship, right? That if the volume goes down, then to compensate, the pressure has to go up, so that the product of the two will always be equal. Does that kind of make sense? And they kind of compensate for each other. All right, so we can do math with this. This is just an equation with 4 different variables. So if I give you 3 variables and ask for the 4th, you can do it, right? So this is directly from your lecture notes. We say, suppose we know we have the pressure of gas in a cylinder that is 600 milliliters. That pressure is 65 millimeters of mercury. If the pressure is increased to 385 millimeters of mercury, what is the new volume? So this is pretty straightforward. We have this formula, which has 4 variables: initial pressure, initial volume, final pressure, final volume, right? And so long as we can assign properly, initially, this is my initial, so this is volume 1. Milliliters is a volume. This is initial pressure, and then the pressure is increased. So this is my final pressure, and they want to know the new volume, so they're looking for V2. Do those assignments make sense? Do you guys agree with that? Okay, and they want to know the new volume, so we're going to solve for V2. And so again, we want it by itself and on top. It's already on top. So if we divide both sides by P2. Oh, hang on a second. You know what? I want to keep this guy here. Okay. So we're going to solve for V2 by dividing both sides by P2. There we go. Right, like that, move it over, divide both sides by P2, that's going to solve for V2, and now we can just plug in, observe my P1 was 65 millimeters mercury. Now I know you're doing algebra, but I still want you to use your units. That's important. And then the P2 was given was 385 millimeters mercury. You'll notice that as you leave your units, you can still do math with the units. It'll still help you know if you did it right. So millimeters of mercury will cancel. You'll be left with milliliters, which is a unit of volume, which is what they wanted. So we're pretty sure we did it right. And we plug it in, 65 times 600 divided by 385 gives us our new volume of 101 milliliters. And we know it's units of milliliters because that's the one that didn't cancel, right? Does that make sense? Perfect, perfect. All right, before we go on to the next gas law, I want to bring us back up here to our kinetic molecular theory and explain why is it that if we decrease the volume, we can expect the pressure to increase. What does this have to say about why Boyle's law would be a thing? Remember, Boyle's law says that as pressure increases, volume decreases, or you could say as volume increases, pressure decreases. So we're looking here at the kinetic molecular theory, and we want to know, how can you explain what's going on with this observation, this Boyle's law observation? How can you explain that using what we know about the kinetic molecular theory? Okay, so this is, okay, so we know that, hang on, volume is the space that it takes up, right? By the gas. What is pressure again? I didn't write it down here. Pressure is collisions, right? It's the force exerted by collisions. So what happens as we lower the volume in our little syringe? Let me copy that up here. We open the syringe, we stick our thumb on it, and then we try to close the syringe. Then we take this sample of gas in this chamber and we give it less space. And when it has less space, then you have the same number of gas particles running around in a smaller amount of space. There's going to be more collisions. It's more concentrated. So there's going to be more collisions between the gas particles and the walls. And increased number of collisions means increased pressure. So therefore, lower volume, increased pressure. Does that make sense? It's not, well, you guys are cute. Okay, it's not a matter of number 2 is explaining this, or number 3 is explaining this, or number 4 is explaining this. It's a matter of saying kind of a combination. We know that they are compressible. That's how you can change the volume, for instance, right? And that it doesn't really say anything about the fact that pressure is a force exerted, right? We do see that there are collisions, but it doesn't say, yes, you'll get more collisions when you compress it into a smaller space. So it's kind of a combination here, right? You can compress it because they've got lots of space between them. When you do compress it, then you're going to get more collisions, and those collisions are going to exert a force on the area. Does that make sense? Okay. All right, we're at about the hour mark, so let's take a quick 5-minute break, and then we're going to come back and continue on with our individual gas laws. All right, any questions on Boyle's law before we continue here? Okay, then we are looking at Gay-Lussac's law. Oops, I need. Again, I'm never going to test you on the names. That's more of history than anything else. But this is named after the French chemist Joseph-Louis Gay-Lussac, who studied the relationship between pressure and temperature. And so he discovered that for a sample of gas at a constant volume, then pressure and temperature are directly related. All right. So what that means is that if, for example, looking at your pressure, that is directly related to or directly proportional to the temperature. So if your pressure goes up, your temperature will go up, or vice versa. If your temperature goes up, then your pressure goes up. It's more likely the case of that, okay? So we're gonna play the same little game that we did here and say, I don't like that little tilde. If I put in a little placeholder K, this is a different K, just some constant times that temperature, then it can become equal instead of just directly proportional. And then if I divide both sides by T, then P divided by T is going to equal some constant K. And since that will always be constant, then my P and T in my initial conditions are going to equal my P and T in my final conditions, like this. And we find that our initial P divided by our initial T is going to be equal to my final P divided by my final T. Like this. So this is Gay-Lussac's law, just like this was Boyle's law here. A functional piece that we get from that. Okay. So again, this is essentially showing us that as your temperature goes up, your pressure is also going to go up, right? And vice versa, as your temperature goes down, your pressure also goes down. Every one of you has probably experienced this at some point in your life because you guys are human beings, and kids have balls and balls get left outside, right? So you've got a basketball that gets left outside, and you're not, taking super good care of it because you're a kid and you don't know any better, right? And after a while it gets kind of flat, but you'll notice that if you go out and look at it in the morning, maybe you kind of poke it on your way to school in the cool hours of the early morning, it's like really flat. Or when you come home from school in the afternoon and you poke it when it's been sitting in the sun and it's really warm, then it's actually like got a little bit of pressure. You guys ever noticed anything like that? Or maybe it was just something like you had a water bottle and you left it in the car on a really hot day and it exploded on you, right? So, because the pressure went up. So this is a closed system, so that's at a constant volume. That's an important part of it. Both of these are closed systems. And so what happens as the temperature goes down in the cool mornings, then the pressure goes down. And it's easy to kind of dent that basketball. And then the afternoon, as the temperature goes up, then the pressure goes up, and then it actually regains at least a little bit of its pressure than it had before. Okay, so let's look up here really quickly. What is it about the kinetic molecular theory that will help explain why it is that when the temperature goes down, the pressure goes down, and vice versa? And you're going to have to be able to explain like this on the test. So not just having memorized this, but understand what they mean. Understanding what they mean is part of kind of tying them into our individual laws here. So if we've got temperature and pressure, again, it doesn't say a lot about pressure except that we've got collisions is pressure. We know that. But it does say this about temperature, right? The kinetic energy is proportional to the temperature. That's the movement energy. Nicole, exactly right. As you increase the temperature, the particles have more kinetic energy. They move faster. And that speeds up the rate of collisions because they're moving faster. But it also speeds up the, if you are moving faster, the strength of the collisions will be greater as well. And vice versa, as the temperature goes down, your gas particles start moving more slowly and with less energy. So collisions happen less frequently and with less energy. Does that make sense? Excellent. Okay. So this is just another algebra equation with 4 variables. So if I give you 3 variables and ask to solve for one, then we can do that. All right. So this is from your lecture notes. We've got a pressure inside of a basketball at 10 degrees Celsius in the evening is 720 millimeters of mercury. The next day after sitting in the sun, the temperature is 34 degrees Celsius. Now we want to know what's the internal pressure of the basketball after sitting in the sun. So for this problem, hopefully you guys can see this is the initial temperature, that's T1. This is the initial pressure, there's P1. The next day after sitting in the sun, our temperature is this one, that one's T2. It's very easy to get them mixed up, so it's important to kind of label them and make sure. Internal pressure, that's what we're looking for, right? P2, the next day. Everybody agree with those? All right. And if we're solving for P2, what do we need to do to solve for P2 for this equation? Remember, to solve, we need it by itself and on top. So the P2, which we're solving for, this one right here, is already on top. So that's nice. So we just need to get it by itself. We need to get rid of the T2. So Nicole is exactly right. If I multiply both sides by T2, there we go. Then these will cancel and I'll have P2 by itself, right? So we're going to say T2 times P1 divided by T1. So we're careful to label each of these. And I'm going to tell you guys, it's easier to solve this problem while everything is still a variable than it is to plug in the numbers and then solve it. So that's always the way that I'm going to do it. So when we do that, we find we want T2 on top. That's 34 degrees Celsius. Uh-oh, I've got a problem, guys. I can't use degrees Celsius in this problem because I have to be able to divide by a temperature. And even though these aren't 0, Celsius can be 0, and I can't use anything that could ever be 0. So Nicole's exactly right. Before I do anything else, I'm going to convert to kelvins, right? So T1 is 10 degrees Celsius, and to convert that to kelvins, I'm going to convert from Celsius to kelvins. I'm going to add 273.15. Okay, so that's going to be 283.15 Kelvin. And this is 34 plus 273.15. Okay, that's 307.15. Let's plug that in here. Okay. Whew. Almost made a terrible mistake there. All right, so T2, 307.15 K. Multiply that by P1, that was 720 millimeters of mercury. divide that by T1 to 83.15 K. One of the most common mistakes that I see made here is students forget to convert to Kelvin. The next most common mistake is to swap which one has T1 and which one has T2. It feels like you want to put the T1 next to the P1, but that would be wrong, right? You've got to put the T2 next to the P1. So if I plug this in, note that I kept all of my units, and because I did, I can see that Kelvins cancel, and the units of my answer as calculated will be in units of millimeters of mercury. Okay, 307.15, multiply that by 720, divide that by 283.15, and I get 780 millimeters of mercury. Here we go. So here you can see if atmospheric pressure is 760 millimeters of mercury, then in the evening here, it was less than atmospheric pressure. Like you would be able to kind of dent that, it would be very soft. And this is greater than the atmospheric pressure. So it would actually be a little bit firm. Does that make sense? Zach says, anytime we see Celsius, should we convert to Kelvin? And yes, absolutely. In this entire chapter, you cannot do any of these equations using Celsius. You always have to convert to Kelvin. Good. Okay, and again, the reason that you could explain this using the kinetic molecular theory is that pressure is collisions and temperature is kinetic energy, right? So if you increase the kinetic energy, you're going to have stronger and more collisions, and if you decrease the kinetic energy, you'll have fewer and less strong collisions. So your pressure goes down as your temperature goes down, and vice versa. Okay, all right, next we have Charles's law. Oops, I thought I made that black. Okay, so Charles's law is named after Jacques Charles, who was another French chemist. Joseph Louis Gay-Lussac also studied the relationship between volume and temperature, but he gave credit to Jacques Charles because he referenced some of his previous work. And here he's looking at the relationship of volume and temperature. So this is at a constant pressure. Now, volume and temperature are directly related. So this was at a constant volume, like you've got a basketball or a closed water bottle kind of a thing. But at a constant pressure, this would be something like a piston, right? Maybe you have a closed system here, but you have this movable piston on top, right? That can move up or down to expand or contract. And you've got, of course, the atmospheric pressure on it, and then you're just looking at how, that balances out with the pressure around. Another image of this that might make sense would be a balloon. It's not a perfect example, but because a balloon is flexible, right? It can expand and contract under the constant pressure around it. So what we see here, volume and temperature are directly related. That means that as the volume goes up, as the temperature goes up, the volume goes up. Say volume directly related to the temperature. And again, we can say that means that volume equals to some constant times temperature. And if we divide by temperature, we'll see that the volume divided by the temperature is going to equal that constant there. Which means because that's constant, my initial volume divided by my initial temperature is equal to the final volume divided by the final temperature. So hang on. So my initial final. So this is the same kind of math that we've been doing previously. All right. And again, this means that as the temperature goes up, under constant pressure, the volume will go up. And vice versa, if the temperature goes down, a different color, then the volume will go down in both of these systems. Okay. So for instance, if I take this balloon and I blow it up, and it's a certain volume, and then I stick it in the freezer, put the temperature down, then if I come back a couple hours later and pull that balloon out of the freezer, it should be smaller than it was before. The volume has gone down. And as I leave it on the counter and it heats back up, then the temperature goes back up to where it was, and the volume will also expand back up to where it was. This is a super easy science experiment to do. If you've got a balloon in a freezer, you can investigate Charles's law. And it's kind of fun to do with kids too. So if you've got kids in your household, then you can do that. Same thing with this guy. If you've got a cylinder and some gases in here, if you heat it up, then this stopper will, it's not a stopper, this, there's a word for it that escapes me. This slidey thing is going to move up to expand. And then as you cool it down, it's going to move back down to give less volume, if that makes sense. How do you explain this using the kinetic molecular theory, using the concepts we've discussed so far? Let's scroll up here. Oh, Zach, great. You've got a great start to this. Yes. Okay, so as the temperature goes up or down, as we saw with Gay-Lussac's law, the kinetic energy will go up or down, right? So temperature goes up, kinetic energy goes up. That means we get more collisions, higher pressure. And because you're in a flexible system, that higher pressure is going to push outwards and expand to give you a larger volume. Right? And contra that, as your temperature goes down, your kinetic energy goes down, your collisions are fewer and they're less strong. And so the outward pressure exerts more force and compresses it until you're back to that equilibrium. Essentially, the equilibrium you're looking at here, is you've got the internal pressure of the gas on this inside surface of this balloon, on the external pressure here. So when they say at constant pressure, they're talking about constant external pressure, right? So the constant external pressure is exerting a certain amount of force, and if you decrease the force exerted here, then that's going to shrink the balloon until the force being exerted on the inside is equal to the force being exerted on the outside. And the same thing here. This is constant external pressure, right? If you heat this up, then you're going to increase the pressure here, which is going to push it outwards against there. Does that make sense? You guys with me? Nicole and Zach, you were on the right track there. So when your temperature increases, your pressure increases, and because you're flexible, then that increase of pressure actually it gets converted into an increase in volume instead. Another great example of this is the hot air balloon. Because what happens is that it doesn't have a different gas. It's just air. It's just air, and it gets hotter, right? But when it gets hotter, then it expands. And because it is expanding, then it's less dense, right? So the density equals mass divided by the volume. Right? Grams per milliliter, or in the case of a gas, you're looking at grams per liter, kind of a thing. And if your volume goes up, because that's in the denominator, your density goes down. And then of course, if you're less dense, you float, right? So you increase the temperature, which actually increases the volume, which decreases your density, and then your hot air balloon begins to float. And so if you want to bring it back down, one of the things you do is you just let it cool off, right? As the temperature goes down, the volume goes down. As the volume goes down, your density goes back up, and you start to fall slowly. Controlled fall out of the air. Are you guys with me? You're very quiet today. Okay, one of you's with me. All right, so let's solve this problem. Here we go. It's the weekend, right? So we could be a little tired. I say it's the weekend, it's only Thursday morning, but we don't have class till Tuesday. So for this class, it's the weekend. All right, let's assign this. A hot air balloon has, that's got to be V1, right? That's my initial volume. And 56 degrees Celsius, that's my initial temperature. And what temperature is the balloon? That's what we're looking for. That's going to be T2. As the volume decreases to 875, this is V2. And again, I always recommend just labeling these before you plug anything in. It'll keep you from putting, because you have two different volumes, two different temperatures, it's easy to get them mixed up. Okay. What else do we need to do before we can solve this problem, guys? We can convert to milliliters. We don't have to. These are both in liters, so they'll cancel. They'll be just fine. But we do need to convert to Kelvin. Yes, we can't use Celsius. Okay, so 56 plus 273.15. Obviously, I'll give that to you, but you're going to have it memorized by the end of this. That gives us 329.15 Kelvin. Okay. So that was the first thing we need to do. The first thing we needed to do was label which one was what one. And the second thing we needed to do was to convert to Kelvin. And now the third thing we need to do is solve for the T2 before we plug anything in. It's so much easier to manipulate these guys than it is to manipulate 955 liters and 329.15 K and 875 liters. It's just simpler. So again, to solve for T2, we have to get it by itself and get T2 on top. Okay, this is tricky because it's on the bottom. There are a couple of different ways to do this, but I'm going to do it stepwise. It's a little bit more tedious. Divide both sides by multiply both sides by T2. That gets it on top, right? And that'll cancel. Good. And now that it's on top, I need to get it by itself. So I'm actually going to have to multiply both sides by T1 as well. Multiply by T1. And when I do that, my T1s will cancel here. And then I'm going to divide by, I'm doing all these in a different color so you can kind of see the order I'm doing it here. Sorry if that's confusing. Divide both sides by V1. And then my V1s will cancel. So I get T2 all by itself over here, and it's on top. So let me just simplify that. So T2 here is equal to V2 T1 divided by V1. All right, that's one way of doing it. That's kind of a stepwise going through the process. Now, let me show you a couple other ways that you could do it, okay? Another way to do it is to just get it by itself, but not on top. So divide both sides by V2. If I do that, right? That gives me V1 over V2 T1 is equal to 1 divided by T2, right? And then I can just observe it's by itself and it's on the bottom, so then I can just flip it. If you see that, if I flip both sides, then I get V2 T1 divided by V1. And then I get T2 on the other side. Okay, that's not all. That's the same answer, right? Feels a little bit simpler. Same thing. But you do have to remember that part where you flip it, okay? Now, many of you will be familiar with this next method. I'm just showing you different methods. I don't care which one you use, but I want you to pick one that feels the best to you, the most comfortable, and stick with it. Because if you're more comfortable with it, then you're less likely to make a mistake, but they're all totally fine. This method is a cross multiplication method, and it's used to just kind of get rid of the fraction altogether before you even get started. So you just do this x, and you're going to multiply those two things together, and you're going to multiply these two things together. And if you do that, you get T2V1 is equal to V2T1, right? You just put everything on top. Just do cross multiplication to get everything on top, and now just get T2 by itself. You're going to divide both sides by V1. V1. Oops. If you do that, your V1s will cancel, and you're left with T2 is equal to V2T1 over V1. Does what do you guys like better? Do you like the flip it method, the cross multiplication method, or the doing it stepwise method? Yeah, the cross multiplication method, often students really like that. Now, it actually makes things a little bit more complicated. If you were solving for the thing on top, you wouldn't, it actually gives you an extra step. But if you're solving for the thing on the bottom, it's really slick way to just get everything on top and then solve for the one thing. Yeah. All right, well, now that we have done this 3 different ways, let's plug it in. So we need, we need a darker color is what we need. We need a color I can see. Okay, we need V2, which I said was 875 liters, times T1, which I said was 329.15 K. Ooh, I'm running out of space. And we're going to divide that by V1, which I said was 955 liters. All right, and then I'm going to plug it in. 875 times 329.15 divided by 955, and my new temperature is 301 Kelvin. Now, unless I say otherwise, you can just leave it there, right? I asked for temperature, you gave it temperature. But if I asked for Celsius, then you'd have to convert that back to Celsius. Does that make sense? All right. Last one. Last law here. Avogadro's law. Same Avogadro that Avogadro's number comes from, right? After the Italian chemist, what was his name again? Amedeo Avogadro is not long enough. His actual name was Lorenzo Romano Amedeo Carlo Avogadro, Count of Caragegna and Saretto, and I probably butchered that. I apologize, but that's Avogadro. We may as well say his name. Okay, so his observation was that at a constant pressure, and temperature. The volume of a gas is directly proportional to the number of moles it contains. Now, at first glance, this is going to seem like a really obvious statement, right? I mean, you're saying the more particles I have, the more space it takes up. Whoa, crazy talk. I can't believe you actually had to state that. But the really interesting thing about this law is that it's the same for all gases. It is so weird. It doesn't matter whether I'm talking about a mole of carbon dioxide or a mole of water or a mole of sulfur hexafluoride or a mole of helium. 1 mole of any gas at constant pressure and temperature has the exact same volume of a mole of any other gas. And that's kind of weird. Isn't that weird? It's weird. In fact, we have one here that we'll just kind of memorize. 1 mole of any gas at standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of pressure, equals 22.4 liters of space. Any gas, right? So you could compare helium, for instance, which has tiny particles with an average mass of 4 grams in a mole. And you compare that to sulfur hexafluoride, which has a mass of, I'm gonna totally, whoops. This is not, I'm gonna look it up. I was gonna estimate it. But I'm here, it's easy. 146 grams per mole. And everything in between, like for instance, air, which is mostly nitrogen, 28 grams in a mole. Doesn't matter how much it weighs. 1 mole of each of these takes up 22.4 liters. I could just have a mixture too, like air, which is 80% nitrogen, 20% oxygen, tiny fraction then of water and carbon dioxide, and still a mole of air particles takes up the same amount of space. That's weird. Okay, but why? Can we explain it using our kinetic molecular theory? Perfect. Nicole, you are exactly right. So there's 2 things to observe here, but the first is this. Yeah, sulfur hexafluoride is like a big honking molecule and helium is a tiny molecule, but the fact is the amount of space occupied by the gas particles is so small compared to the amount of space between them that you don't even notice it. It doesn't even matter that sulfur hexafluoride is bigger. It's still a gas, and the amount of space between the particles is a bigger consideration. Great. The other consideration is, as we mentioned here, even though some of these might be nonpolar and something like water might be polar or have hydrogen bonding in the gas phase, they're so far apart that they don't have any attractive or repulsive forces. And so it doesn't matter what the gas is made out of, they all behave exactly the same way. Perfect. Excellent. Okay, so based on this interesting observation, here's the question that I have from the lecture notes. Which sample contains more gas particles, a liter of neon or a liter of HCl gas? They're the same. Exactly. They are the same because it's liter of gas, even though I've got twice as many particles here, twice as many atoms, it's just 1 molecule versus right? So gas particles, this is neon gas particles, HCl gas particles. They have the same number of particles, even though this has the same, like twice as many atoms in there. Okay, perfect. All right, that is it for your individual gas laws here. So let's head on over to your worksheet. We've got about 10 minutes. We can look at these individual gas, let's see, problems, gas law problems. So I've got 4 problems. Each of these corresponds to one of the individual gas laws that we have just been investigating, okay? So we want to determine which one is which and then solve, insofar as we have the time. So before we solve, let's go through here and say which gas law are they looking at. This one is telling us the initial pressure and volume is this, and we want to know the final pressure after the volume has been compressed. Which gas law is this? Perfect. Yep, it's Boyle's law, which again, I'm never gonna have you memorize that specifically, but that's the P1 V1 is equal to P2 V2. Note that I didn't say here specifically, I'm at a constant temperature, but if temperature is not mentioned, then you can presume you're at a constant temperature, right? And so you're gonna plug in, this is, we've got these pieces here. So they gave us V1 there and P1 there, and this is V2. And then we're solving for P2, right? So we're going to divide both sides by P2. And we're going to see V2 as P1 times V1 over P2. That's going to be 1 atmosphere times 2.85 liters divided by P2, which was, oh, I'm sorry. We're not solving for V2, we're solving for P2. We want V2 on the bottom here, 1.70 liters. Okay. Back up, back up, back up. We're going to divide both sides by V2. There we go. That's going to solve for P2. I plug it in. My liters cancel as well, right? So 1 atmosphere times 2.85 liters divided by 1.70 liters gives me 1.68 atmospheres. That's my answer. Does that make sense? So Nicole looked at this and said they only gave us information on pressure and volume, so it's got to be that one law that has to relate to pressure and volume. And that's all, right? What about this one? An aerosol can has an internal pressure of 3.85 atmospheres at 25 degrees Celsius. What temperature would cause the can to become materially compromised? That is to say, potentially explode by reaching a pressure of 6.50 atmospheres. By the way, this is really dangerous, but it's the kind of thing that I hear happens at like scout camps, right? Ho, 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 I have a campfire and I have an aerosol can. Let's toss it in and see what happens. Everybody should dive so that they don't get hit by shrapnel when it explodes. But they gave us a pressure here, right? And that is a temperature. And then this is my P2, and they're looking for what temperature? That's T2. Okay, so what am I going to use here? Perfect, Nicole. Yes. P1 over T1 equals P2 over T2. I think this was Gay-Lussac's law. I don't remember. It doesn't matter. I'm not testing you on that. Honestly, I'm not testing you on it because I can't be bothered to memorize it. I'm not going to test you on something that I won't memorize myself. Okay, so remember, we have to convert to Kelvin first, and then get T2 on top second. So these are the two things we need to do to answer this question. I'm gonna let you guys practice that yourself and solve for this one so that we can at least look at these before we let you go for today. Okay, so down here, a balloon has a volume of 43 liters at 20 degrees Celsius. What is its volume at -5 Celsius? Let's see, what's your new temperature? Looking for the volume. It's not hard if you can just recognize, oh hey, Celsius is a unit of temperature, liters is a unit of volume. Once you can pick these apart, you can say, okay, what was that formula that compared volume to temperature? Again, no pressure is mentioned, so you can presume that it's at a constant pressure. What's the equation we need? Perfect. I think that one is Charles's law, right? V1 over T1 equals V2 over T2. Good. Again, we want to get volume by itself and make sure you convert to Kelvin on your temperatures, and you can solve that one. Good practice. Okay, so if we have done Boyle's law and Gay-Lussac's law and Charles's law, that tells us that this one is wanting Avogadro's law. And Avogadro's law says that 1 mole of any gas is equal to 22.4 liters at STP. And here I have a volume of 16.5 liters at STP. But they want to know the mass. They want grams. So this is tricky. Hang on a second. So number one, I want grams of CH4. And number two, they gave me that I have a 16.5 liter sample at STP, and I know that at STP, any 1 mole is going to be 22.4 liters. So I could go from liters to moles because they're both at STP, but how do I go from moles to grams? The molar mass, can't forget that. All right, periodic table, carbon is 12.01, and I've got 4 hydrogens, each at 1.008, so 16.042 grams at a mole. If you thought we were done with molar mass and mole conversions just because we took exam 3, you are wrong. We will never be done with mole and mass conversions in this class. Okay, so now this is just a dimensional analysis problem that includes this observation for Avogadro's law. And we can go from the volume to the mass. Okay, I will let you guys do that, and I'll let you guys go. I hope you have a great weekend, and I'll see you on Tuesday. Okay, so following up from Thursday here, where we looked at individual gas laws and we practiced using those, today we are going to actually start with the combined gas law and then move into the ideal gas law, and then we're going to look at partial pressures. So the combined gas law actually looks at these relationships, right? Boyle's law looked at just pressure and volume. Gay-Lussac's law looked at just pressure and temperature. Charles's law looked at just volume and temperature, and the combined gas law puts these all together and says instead of holding one thing constant, like temperature or volume or pressure, then what if all three of those were variable? Then what would it look like? Well, we already know what these relationships are, right? So if we put it all together, we get the combined gas law. We'll start a new section up here. Need a little more space. There we go. Okay, the combined gas law. It combines all of those other laws that we saw, right? So it combines, we had P1 V1 is equal to P2 V2, right? That was Boyle's law. And then we had P1 over T1 is equal to P2 over T2. This was Gay-Lussac's law. Just looking at the relationships between pressure and volume. And then of course we had V1 over T1 is equal to V2 over T2. Right here. Oh, Sarah's on top of it. Yeah, so if we take all of these and put them together, right, each of these is kind of describing a relationship. You can see that you're going to keep the P1 and the V1 together, and you're going to divide those by T1. And then that's going to equal, again, the P2 and the V2 together, divided by the T2. Do you guys see how you could come up with this combined gas law? If you kind of put all these together, you're going to get that guy. And the nice thing is, if you wanted, you could just memorize this one equation, right? So Erica says, do I have to memorize the equations? If you just memorize this one equation, then if I give you a problem that says I'm at constant volume, then you can just eliminate the volume and you're left with Gay-Lussac's law. Hey, cool. Or if I give you one that's at constant temperature, you can just eliminate the temperature and hey, look, you've got Boyle's law. Or if I give you, obviously, a constant pressure, you can eliminate the pressure, they cancel, and then you've got Charles's law. Does that make sense? It's like way easier to memorize just this one and then use that to answer any problems with either the combined gas law or individual gas laws. It'll make your life just a little bit easier. Okay, but we have to do math with this, right? It's not enough to know the gas law. You have to be able to solve a problem. So this is from your lecture notes. And what we see is now we have 6 variables. And if I give you 5 and ask for 1, we should be able to solve for that, okay? So I've got 3.5 liters of gas collected at 25 degrees Celsius and 745 millimeters of mercury. So all of these are the initial conditions. And then I give STP, and you do have to remember what that really means is standard temperature, 0 Celsius, and standard pressure is 1 atmosphere, right? And then they want to know the volume. So let's kind of label this here. We've got, that's volume, right? So that's my V1. And then this is my initial temperature, so that's T1. Sarah, you've got a question, but I'm not sure I understand what you're saying. Can you reword that? This is my initial pressure. It's in millimeters of mercury. And then I've got standard temperature, so that's my T2. And that's my P2, and they're wanting V2. Okay. Oh, great question. Okay, sorry, Sarah. I think I'm understanding what you're asking now. So if there's not one thing that's constant, right? If I say I'm at constant temperature, then you could eliminate the temperature and just use the shortened version, which is Boyle's law, right? But if everything is changing, right? My temperature went from 25 to 0, my pressure went from 745 to 1, then my 3.5 liters is going to go to a new volume. If everything is changing, I have to use this one. Yeah. STP, this was just what I used for this problem. I could use STP for any other problem. If there's STP, it doesn't necessarily mean that I'm using the combined gas law or any other gas law. You just have to know that STP stands for standard temperature and pressure. In fact, I'll write that down here. Hopefully that makes sense. Okay. All right, so we're going to solve for V2. And I did tell you guys, this is very important. This will make your life easier. Solve for V2 before you plug stuff in. So if we want to solve for V2, this guy right here, remember the rules are you have to get it by itself and we have to get it on top, right? Now, it's already on top, it's already in the numerator, so that's not too bad. We just have to get it by itself. So I'm going to, great, yeah, that's right. I'm going to multiply by T2. And I'm going to divide by P2. I'm going to do that on both sides. Because if I multiply by T2 and divide by P2, then my T2 should cancel and my P2 should cancel. I should probably do this separately. Okay. We'll save that for other problems. Okay, so I'm going to multiply by T2 over P2. I'm going to do the same thing. I'm going to be lazy and just copy that over. Multiply that. Okay. So when I do that, my T2 cancels and my P2 cancels. So now I've got V2 all by itself and it's still in the numerator, so I'm good. So this is the formula I'm going to do. T2 times P1 times V1 divided by P2 times T1. Okay, great. So now I can plug it all in, right? So my T2 is 0 degrees Celsius. Did I do that? That's 0. And then my P1 was 745 millimeters mercury. And then my V1 was 3.50 liters. And then my P2 is 1 atmosphere. And then my T1 was 25 Celsius. Oh, Sarah, you are exactly right. Thank you for catching that. I was just waiting for somebody to catch that. So there's two very important things. The first is we cannot use Celsius. You notice actually, if I plug all this in right now, I'm going to get an answer of 0. That won't be helpful, right? We have 0 volume. Where did the gas go? I don't know. But hopefully you can see like Celsius will never be okay. You always have to use Kelvin. Not just because it's not going to help to multiply or divide by 0, but also like you couldn't have a negative volume, whereas you can have a negative Celsius. So that won't help. So let's see, to convert from 0 degrees Celsius to Kelvin, we've got a formula, and of course it's on your equation sheet. We're going to add 273.15. So this is 273.15 K. And then 273 plus 25 is going to be 298. Right? Okay, so I'm going to plug. Yes, Zach is just confirming STP means 0 Celsius and 1 atmosphere. Yes, that's exactly what it means, always. Always, always. There we go. We fixed our temperature. It's got to be in Kelvin, otherwise we're not going to get the right answer. What else is wrong with this setup, though? There's something else we're missing. Great, Nicole sees it. Perfect. We have atmospheres on the bottom and millimeters of mercury on the top. So if I go to try to cancel out my units, I'm actually not going to be able to cancel those out. So it actually, for the combined gas law, it doesn't matter whether we use millimeters of mercury or whether we use atmospheres. We just have to be consistent. So it doesn't matter which. So let's do this. Again, it's on your equation sheet. 1 atmosphere is equal to 760 millimeters of mercury. So that'll just be really easy to plug that in. We'll use that guy. And I want you guys to know, even though I'm doing, we could say algebra here instead of dimensional analysis, the only way you guys saw that issue was the fact that the dimensions didn't cancel. So even though I'm not technically doing dimensional analysis, like I'm still analyzing my dimensions. I'm still actually doing dimensional analysis, even though I'm setting up the problem as a typical algebra problem, because that's going to show me where my problems are. So now I can plug it in. So let's see here. Both Sarah and Nicole got 3.14 liters. Okay, let's plug this in. 273.15 times 745 times 3.5 divided by 760 divided by 298.15. And wait a second. Oh, I did 0.35 and not 3.5. Okay, yes, I'm off by a factor of 10. 273.15 times 745 times 3.5. There we go. Divided by 760 divided by 298.15, 3.14. You guys are right on 3.14 liters. Perfect. Any questions on that one? Okay, let's do one more. Okay, so I'm just going to pull this from your worksheet. I'm looking at section 3. We're going to look at a sample of gas that has a volume of 735 milliliters at a pressure of 1.2 atmospheres at a temperature of 112 degrees Celsius. If we want to know what is the volume of the gas at 658 millimeters of mercury and 281 K. All right. Well, as you can see, we're given volume and pressure and temperature, and we're given a new pressure and temperature, and we want to know volume. So they've given me 5 different variables, and they're asking me about something else. So this is your clue. You have to use the combined gas law because the pressure is changing, and the temperature changes, and the volume changes. All right, so we're gonna use this guy again. Now again, oh, you know what? We're not gonna do this one, sorry. Back up. Because we just did one where we solved for volume. Let's do this next one here. So let's do this guy. What is the temperature of this gas at 549 milliliters and 3.29 atmospheres? So again, they give us volume, pressure, temperature, and they want to know temperature if I have a different volume and a different pressure. So that tells us we're going to use this combined gas law, which has all 6 of those variables in it, from the initial conditions to the final conditions. So that's our combined gas law. Okay, so if we're solving for temperature, let's just this is my V1. This is my P1. This is my T1. It's easy to get lost, so it's good to label them. This is my V2. And this is my P2. Okay. And they want to know T2. What is the temperature? So we have to solve for T2. Again, we have to get it on top and by itself. What should we do here? How do you want to solve that problem? Sarah, that looks great, but I want to know how you got that. We went over 3 different ways to solve a problem like this last Thursday. I think most of you guys liked one method over another, but none of them were necessarily wrong. Okay, so Sarah's gonna say, let's get it by itself first. So she says, let's divide both sides by P2V2. This is the way that I like to do it. Divide both sides by P2V2. And when you do that, your P2's cancel and your V2's cancel. And then you have an equation that looks like this. It says P1V1 divided by P2V2 T1 is equal to 1 divided by T2. And then what Sarah did was that she said, okay, look, I got it by itself, but it needs to be on top, so I'm just gonna flip it. I'm just gonna take the inverse of both of these. And when I flip that, what's gonna happen is, let's see. I'm gonna take everything on the bottom and I'm just gonna stick it on the top. Oops, I need more space here. Take everything on the bottom, stick it on the top. And now I have solved for T2 and it's all by itself and it's on top. That's super convenient. That's probably how I would do it these days. I'm not sure that I could have seen that when I was in college though. So if you want like one of the other methods, that is also totally fine. Again, I encourage you to use the one that you feel the most comfortable with because you're less likely to make a mistake. So Zach says the way he likes to do it is the cross multiplication method. So what he does is he's going to take this guy and he's going to cross multiply. So he's going to multiply these things together, and that's going to be equal to these things multiplied together. That just puts everything on top so that it kind of simplifies your life. And then you have P1V1 T2 is equal to P2V2 T1. Make sure you keep those 1s and 2s straight. And then, now that everything's on top, to get it by itself, T2, we're just going to divide both sides by P1V1. Okay, divide by P1V1. Is that too light for you guys to see? Try to use slightly different colors so you can see my thought process here. Okay, and then your P1V1s cancel here, and now you have T2 all by itself. So you see that T2 is equal to P2V2 T1 over P1 V1. So you get the same answer, right? So whichever method you guys like, there's the cross multiply or there's the move it over and then flip it. And then of course there's the just do everything individually. So you could move the T2 over and then move the P1 V1 T1 over. That's a little bit more time consuming, but whichever one you like works. And now we can just plug this all in, right? Equals, okay, P2. Oh, Erica says no, I can't just plug it on. What's wrong? What am I missing? Oh, I have to go from Celsius to Kelvin. Good catch. All right, so this one I don't have to because that's what I'm solving for. But for 112, 273 plus 112 is going to be 385 Kelvin. Sarah, you are exactly right. The temperature units must be in Kelvin. The pressure and volume units don't have to be in a particular unit, but they do have to be the same, right? So I don't care if my volume is in liters or milliliters, so long as they're the same, so that those units will cancel. And I don't care if my pressure is in atmospheres or millimeters of mercury, so long as the units are the same, so that they'll cancel. So if I had given these to you in millimeters of mercury, which I think I did in part A, then you'd have to take that extra step of converting one of these to the other unit, when it wouldn't matter which. And it's the same thing with the milliliters, right? If I'd given one of these in liters, you would have to convert one to the other. And it doesn't matter whether they're both in liters or both in milliliters, but they do have to be the same, so the units cancel. Good questions, guys. Whoops. Okay, so P2, let's see, that's 3.29 atmospheres. And then V2, that's 549 atmospheres. And then T1 is right up here, 385 K. Divide by P1, which was 1.20. It's kind of lucky I don't have to make any volume or pressure conversions, because that's the kind of thing that I would make you do, huh? Well, V1 is 735 milliliters. Oh, wait a second. I have like too many atmospheres this year. Okay. 549 milliliters. What was I thinking? Milliliters. Watching my units. Analyzing my dimensions. Okay, so my atmospheres cancel, my milliliters cancel. I'm left with Kelvin, which is what they wanted for T2. And so now I just plug this in, right? So 3.29 times 549 times 385 divided by 1.2 divided by 735 gives me 788.43. Now I have a slightly different answer than you, Sarah, because I rounded the 385.15 down to just 385. It's still basically the same value, right? It's still basically 788 Kelvin. Okay, and then if you want to convert, so 788, subtract that 273.15, you get about 515 Celsius. Now, whichever one you report is just going to depend on what I'm asking for, right? So like on the test, you'll see whether the answers are listed in Celsius or Kelvin, and that'll tell you whether you have to convert back or not. Does that make sense? You guys with me? All right, that's it for this section. I'll let you guys go. Have a great day.